I am Harry Shepard of the Westinghouse Electric Corporation and Vice Chairman Technical of the 14th Electrical and Electronic Insulation Conference. This conference, which is co-sponsored by the Institute of Electrical and Electronic Engineers and the National Electrical Manufacturers Association, is pleased to be able to sponsor videotaping of outstanding technical papers so that they are available for viewing by industry, universities, and government. Now, I am pleased to introduce to you Dr. Robert Hebner of the National Bureau of Standards, who will present his paper titled Streamers in Liquids, Basic Phenomena and Examples of Their Influence on Apparatus Design and Testing.
This presentation will review the basic phenomena of streamers in insulating liquids, and will give examples of how this basic phenomena influence the design of apparatus and the testing of high voltage equipment and electrical insulation. Okay. I would like to acknowledge the other workers who have contributed to the development of this area of research. Dr. Edward Kelly at the National Bureau of Standards and I have performed most of the measurements which are to be discussed in this program. However, their interpretation was developed in consultation with staff from General Electric, from Exxon, and from the Naval Surface Weapons Center. Specific examples that I chose are from published work from General Electric and from the Naval Surface Weapons Center. In our review of the basic phenomena, it is important to first emphasize the experimental approach. A writer has asserted that any information that can be gained from terminal measurements, that is, measurements of voltage and current in electrical insulation, was understood in the 1930s. This is obviously an addition to the terminal measurements, that is, accurate measurements of voltage and current, measurement of parameters like volt time curves and breakdown voltage. We are also performing optical measurements. Schematically, the apparatus would look as it is shown on this slide. A light source, which is usually a laser for convenience, shines through a test cell which contains the liquid under test and an electrode structure. Using appropriate optics, this light signal is focused into an image converter camera where high-speed photographs are made of the phenomena under study. At the National Bureau of Standards, we have also developed a second approach, a second technique for recording these this streamer activity. This approach is to use an optical delay system. The motivation for this development is the fact that electrical breakdown is a statistical event. One does not know when a system is going to break down. And therefore, it is very difficult to synchronize on a nanosecond time scale the recording of an event which may move around in time of order microseconds. To overcome this inherent statistical nature of breakdown, we have built an image-preserving optical delay system which permits the shutter to be opened only after the breakdown has occurred, and then by adjusting the length of the optical delay, we are able to photograph before, during, or after the streamer propagates across the gap. In the remainder of this presentation, I will be showing photographs, high-speed photographs of the data. I would like to take this opportunity to orient you as to what it is you're going to see and how it was taken. The data was taken primarily using a sphere point or point plane electrode systems. The camera was focused on the inter-electrode region. During a high voltage pulse, 5 photographs were typically made. The earliest, or the first photograph, will be on the bottom of the slides that I'm showing you, and as time would increase as one goes vertically. The first of the basic phenomena that I would like to discuss is the phenomena of the cathode streamer. That is, a streamer initiating from a point cathode and moving to a plane or spherical anode. This photograph shows the high-speed photographs of the cathode streamer event. One sees a small protrusion growing from the point, as you see in the bottom picture. As time goes on, moving upward, this protrusion grows into a bush-like structure. On the center set of 3 photographs, one can see a second phenomena taking place. In the upper 2 frames, one sees a faster, more streamer-shaped event coming from the cathode bush. This can be seen more clearly in the artist's conception, which is simply a redrawing of the data shown on the previous photograph. The phenomena which takes place is a bush-like structure grows from the cathode point. When this reaches a certain and somewhat unspecified size, a much faster event occurs. This event is supersonic and is roughly a factor of 10 faster than the growth of the bush-like structure. When this faster event makes contact with the anode, the breakdown is initiated. Here we show a photograph taken approximately 50 nanoseconds after breakdown has taken place. This photograph shows a few of the features that I wish to emphasize. One is, first, that the bush-like structure grows from the point cathode, which is easily seen in this photograph. Second, the streamer propagates from the bush to the anode, causing breakdown. And I would like to emphasize that the streamer is indeed, in this case, propagating from the bush to the spherical anode. This can be seen by observing the V-shaped shock wave which occurs. If the streamer were propagating from the anode to the cathode, the shock wave would be reversed. So this photograph not only shows the basic phenomena, but it also shows the direction of propagation. I should also like to point out, for completeness, that in highly purified fluids, this fast cathode event does not exist. The fast cathode event seems to be, with the data that we have so far, somehow related to the degree of chemical and/or physical purity of the fluid. So we have reviewed what happens when a point is the cathode. Now let's reverse the situation and consider what phenomena take place when the point is the anode, and we have anode streamers. Here is a photograph showing anode streamers. The first and most obvious difference that one sees in this photograph as the one shown for cathode streamers is that the streamer propagation is much more rapid. Looking again at the center set of frames, in the bottom 2 frames there is virtually no streamer activity which can be observed. In the 3rd frame from the bottom, the streamer fills about half of the inter-electrode region. By the 4th frame, breakdown has taken place. So whereas with the cathode streamer, it took a full 5 frames for breakdown to take place, with the anode streamer, it only takes 1. And so the anode streamers are faster than the cathode streamers by about an order of magnitude. For clarity, we again show an artist's conception of the breakdown from an anode point. The drawing shows 4 points separated in time. One can see the anode bush growing from the anode electrode, the point electrode, which is the anode in this case, and branching, being much more branched than the cathode streamer, and growing across the inter-electrode region. The point to be emphasized here is that these anode streamers are about an order of magnitude faster than the cathode streamers were. This single frame photograph shows breakdown from an anode point at approximately 20 to 50 nanoseconds after the breakdown has occurred. One can see a well-formed anode streamer, almost hemispherical in shape, having grown from the point anode, and the dark channel is the first breakdown path. This is where contact was made, where the streamer made contact across the interelectrode region. We have now reviewed the properties, the shape, the relative propagation velocities of cathode streamers and of anode streamers. This type work has been going on for approximately the last 10 years throughout the United States and the world. I would like now to focus on another area of measurement, another physical property which can be measured, for which the measurement is very new. This work has all been done within the past year. That is a measurement of the dynamic electric field distribution in the interelectrode region as the streamer propagates from one electrode to the other. Again, we show high-speed photographs. This time the electrode structure is placed so that the streamer propagates horizontally rather than vertically. If we look at the set of photographs on the extreme edge, where we have 4 clear photographs before breakdown, we see that what we have is a cathode streamer propagating from a point electrode. We also have a fringe pattern in association with that streamer. These fringes are due to the electro-optic Kerr effect and are the phenomena which give us the means of determining the electric field distribution. To see this more clearly, let's again examine the artist's sketch of the phenomena. We show 4 cathode points here separated in time. The earliest time, we see a Kerr fringe pattern caused merely by the fact that there is a potential difference between the point and plane electrode. Now we can consider conceptually 2 different extremes that could take place. First, the streamer could be totally non-conducting. If this were the case, as the streamer propagates from one electrode to the other, there would be no change in the electric field distribution, and therefore the fringe pattern would remain stationary, and we would see the fringes, we would see the trees, the streamers, propagating through the fringe pattern. The second extreme would be if the streamer were a conductor. If the streamer were a conductor, then the electric field distribution between in the interelectrode region would change as the streamer moved from one electrode to the other. And in this case, we would see the fringe pattern actually moving with the streamer. And you can see from the diagram that is the situation. The fringe pattern does move with the streamer, which suggests that the streamer is a conductor. Now we can be somewhat more quantitative than just suggesting that it's a conductor. Let's perform a calculation. In this case, we modeled the streamer as a sphere at the same potential as the point. When we modeled the streamer as a conducting sphere at the potential of the point, the fringe pattern, which is shown in this photograph, was calculated. One can see that there is excellent agreement between the calculated fringe pattern and the measured fringe pattern. To show the sensitivity of the calculation, we also assumed that the potential on the sphere was changed by plus or minus 10%. Under this assumption, the fringe patterns were calculated, and one can easily see that the fringe patterns are significantly different from that was measured during the breakdown event. So what we have been able to measure here is the electric field distribution, and we have shown that the electric field distribution is, to within plus or minus 10%, the electric field distribution which would be obtained if the streamer were perfectly conducting. Now, to provide a background for this last assertion, I would like to demonstrate that the electro-optic Kerr effect is actually capable of measuring the electric field distributions in the test geometries which were used. Historically, the Kerr effect has been used only in a parallel plate type geometry where there is a large region of relatively uniform fields. In the measurements that we have just talked about, there was essentially no uniform field region. In fact, they were best modeled by a sphere plane geometry. So we constructed a sphere plane geometry, applied a high voltage pulse to this electrode system, and measured the Kerr fringe pattern, which is shown on this slide. In a sphere plane geometry, it is possible to calculate the electric field distribution. So we calculated the electric field distribution, and from this calculated field distribution, we calculated the Kerr fringe pattern distribution, which is shown as the computer prediction on the slide. Now, it can easily be seen that the computer predicted fringe pattern and the measured fringe pattern agree very, very well. In fact, the agreement was within our limit of resolution, which was about plus or minus 4%. I should also emphasize that this data was taken using a high voltage impulse, so that there was no space charge distortion in the inter-electrode region. Lest I give you the impression that we have answered all the questions, I'd like to share with you the next two data slides. The slide showing now shows you a anode tree system growing between the inter-electrode region. This is purely a photograph of the pre-breakdown structure of the streamer itself. Now, we also combine that with a Kerr fringe pattern, and we see that we do have light modulation. There are dark regions and light regions. There's a modulation of the transmission of the light wave through the region. However, we have no way of deconvoluting that to determine what the electric field distribution is. We don't know if the electric field distortions are due to space charge in the quiescent fluid, for example, or maybe are merely due to the fact that there are conducting structures in the inter-electrode region, and therefore shielding portions of the electric field of the area, so that the electric field distribution does change as the tree grows. This is an area which is under active analysis right now, and we hope to come up with techniques to deconvolute this information. We have now looked at the electric field distribution in the inter-electrode region. We have looked at the properties of the anode streamers, and we've looked at the properties of cathode streamers. There is one other physical phenomena which we can measure optically concerning the streamer propagation in the fluid, and that is the shock wave propagation. The shock waves are shown best on the photograph, on the set of photographs on the extreme left. We see two different phenomena going on. There is the parallel dark bands which are growing outward in the bottom three frames are the shock wave, the acoustical shock wave. When you set an acoustic detector, a microphone, to listen to what happens at a discharge, that is the discharge noise that one hears. The second phenomena, which you can see in the top 4 frames, is the gas column growing in time as the discharge itself was extinguished, but the gas column itself continues to grow. So we have two different phenomena here. We have an acoustic shock wave that's growing out in the inter-electrode region, and we also have, growing at a slower rate, a gas column. Now, this data is presented on this slide, and it shows that the radius of the shock wave, which is the open circles, increases at a rate which is significantly faster than that of the gas column and is approximately linear with time. The radius of the gas column, which is an order of magnitude slower, is approximately quadratic in time. And these dependencies are consistent with simple mathematical analysis of how the gas column and shock wave should propagate, and further study to try to relate these propagation velocities to things like the pressure and temperature of the arc are continuing. We have now looked at the 4 physical phenomena that characterize present studies of streamers and fluids. That is the propagation characteristics of cathode streamers, the propagation characteristics of anode streamers, the measurement of the electric field distribution, and the measurement of the shock waves. What I'd like to do now is stop and look at some of the applications of this phenomena and to show how an understanding of the streamer behavior has led to improved testing and can lead to improved design of apparatus. The first application that I would like to discuss is the application of a high-powered switch. The switch is shown in the process of breaking down in this slide. The streamers which make contact have started from the anode, because anode streamers are an order of magnitude faster. One also sees illuminated the cathode streamers growing from the cathode, but they have not had time to propagate across the inner electrode region. This switch is designed to hold off several million volts and then, when closed, carry several million amps. So it is a legitimate terawatt switch. The behavior of the switch was modeled by understanding the streamer propagation characteristics. The model which was developed is shown in this slide. The streamer itself is modeled as a resistor and an inductor. Between the tip of the streamer, there is a capacitance and a resistance of the remaining water. This is a water switch. Also, in parallel with the streamer, there is the capacitance and the resistance of the unperturbed water. Now, this model appears to be very simple, but there are two parameters which were critically developed by understanding the streamer propagation in the switch. The first parameter is the time rate of evolution of the point of the streamer. What that basically says is that the capacitance of the water between the tip of the streamer and the adjoining electrode is a time-dependent parameter. The C sub WS shown on the slide is time-dependent, and that time dependence is determined by knowing the streamer propagation characteristics. The second parameter, which is critically determined by streamer propagation characteristics, is the effective resistance of the streamer. The measurements that we have shown earlier have indicated that the streamer is basically a conducting medium. So we know that the resistance of the streamer is a very small resistance. However, we also know from fundamental considerations that the resistance is not zero. There is energy dissipated as the streamer grows because it takes energy to change from a quiescent water into a conducting plasma. That is a dissipation process, so some resistance is necessary. I think that the best effective resistance that was found in there was of order 14 ohms. To demonstrate that this works, I would like to show an experimental curve and a curve that was calculated using this model. The experimental measurement of the voltage across the switch is shown by the solid line, and the dashed line shows the calculation, and the agreement is very, very good. I'm not going to show a lot of other models which gave very poor agreement. Let me just show this model, which used the streamer propagation characteristics appropriately and was able to calculate the voltage across the switch. The second test procedure that I'd like to talk about, a second application, is the determination of the volt time behavior of transformer oil. I mentioned earlier in this presentation that we need to go beyond the measurement of just volt time curves for the material properties of the dielectric. However, it's also important that when we go beyond this, we perform measurements which permit us to get back to the type of characterization that with which we are familiar. This graph shows that it is possible to determine the volt time curve for a practical test fixture in transformer oil from knowledge of the streamer propagation characteristics. The open squares are the points which would be predicted from the cathode streamer velocity, and the X's would be predicted from a point plane as opposed to a rod plane cathode streamer. And one can see that taking those points and putting a line through them, one does a fairly good job of predicting the experimentally measured points. The final area of application that I would like to discuss with you is one which has just been initiated, one that's ongoing, and that is the study of the interfacial behavior in in a liquid-solid system. The first parameter that we're looking for in the interfacial system is breakdown location. To demonstrate this, we show here a photograph showing a parallel plate system with an interface, and we see the breakdown is taking place at a point which is not on the interface. So it is necessary to determine breakdown location. Having determined breakdown location, having determined those situations under which breakdown will occur along the interface, then the second phase of the work is to determine the electric field distribution in the fluid adjacent to the interface, to see how this electric field distribution is different from the electric field distribution in a purely liquid breakdown. The final parameter that needs to be measured is the streamer propagation characteristics along an interface. And again, these need to be contrasted with and compared to the streamer propagation characteristics in a fluid alone. So the measurements at interfaces are to take the streamer propagation characteristic measurements that were made in fluids alone and apply those to measurements along interfaces to say on a more fundamental level why the breakdown along an interface is different from the breakdown in the bulk of the material. So in summary, what we have done is we have reviewed the four parameters of streamer propagation in fluids. We've reviewed the cathode streamers, we've reviewed the properties of the anode streamers, we've reviewed the measurement of the electric field distribution, and we have looked at shockwave phenomena. We have shown how these physical parameters of the streamers can be used to predict the behavior of macroscopic fluid insulated systems.